Noche Cósmica.
There is a moment in planetary history, a threshold moment, when Venus crossed from one fate into another, and everything that came after followed inevitably from that single, irreversible turn. We do not know exactly when it happened. We cannot see it in the rocks anymore, but we can feel its consequences in every breathless measurement taken by the machines we have sent to that world. We can sense it in the way Venus presents itself now, shrouded and hostile, a cautionary twin orbiting just 40 million kilometers from Earth, separated from us not by distance, but by a choice the solar system made billions of years ago. If you have ever wondered why the second planet from the Sun became so unimaginably different from our own world, why it transformed into a place of such extreme pressure and heat that it feels less like a planet and more like the interior of an oven, then what follows is an unhurried exploration of that mystery. If that curiosity about Venus's slow descent into hell fascinates you, I invite you to subscribe so you can return to these slow, accurate journeys through the strangest and most wondrous corners of our solar system whenever you seek that particular kind of knowledge that comes best in darkness and stillness. Now imagine yourself descending through Venus's atmosphere, not falling, but sinking. The descent is gradual, and there is no sound, only the sensation of change around you. You begin at the edge of space itself, in the thin, freezing darkness where Venus's outermost atmosphere bleeds imperceptibly into the void. Here, the temperature hovers near -180 degrees Celsius. The sun, so distant now in your mind, still illuminates the planet below with its patient light. But the rays pass through something extraordinary, clouds so thick, so utterly complete, that they form a veil unbroken by any gap or opening. These clouds are not white in the way Earth's clouds are white. They are a pale, almost sickly yellow, a color like old ivory, or the interior of an unripe lemon. They shimmer faintly, occasionally catching light and reflecting it back into space in a way that makes Venus the brightest object in our sky at certain moments of the year. The evening star, the morning star, that pure, unblemished point of light that guided ancient navigators across oceans. And yet beneath that innocent glow lies something we will soon approach. As you descend deeper into the cloud tops, the temperature begins its slow rise. Not suddenly, but with the inevitability of gravity itself. You pass through the uppermost layers, where the air is thin enough that you might still breathe it, though you would not want to. The clouds grow denser. Their texture changes from a gossamer thinness to something more substantial, more present. The yellow deepens. And here, in these highest clouds where the temperature reaches -60 degrees Celsius, the air begins to acquire a peculiar property. It carries within it microscopic droplets of sulfuric acid, so fine, so dispersed, that they form not so much a substance as an idea of substance, an atmosphere more chemical than air, more hostile than hostile. The descent continues. You sink through layer upon layer, and the pressure around you begins to make itself felt, not suddenly, but insistently. The weight of the atmosphere presses inward from all sides. Imagine standing at the bottom of a deep ocean trench on Earth. That is the kind of pressure we are approaching, but we are not even halfway through Venus's thick envelope. The clouds grow denser still, the yellow brightens into something almost golden, and occasionally you glimpse structure within them, waves, swirls, organized patterns that move with the slow, deliberate rotation of the planet's wind currents. These winds move horizontally, pushing the clouds around the planet in just 4 Earth days, yet the planet itself rotates beneath them so slowly that a single Venusian day, one complete rotation of the world, takes 243 Earth days. It is a strange contradiction, this planet where the winds race around while the surface sleeps in cosmic torpor. As you descend further, you begin to feel the heat. It enters first as a subtle presence, a warming in the thin medium around you. 50 kilometers above the surface, the temperature has risen to a pleasant 20 to 30 degrees Celsius, not unlike a spring day on Earth. Were you truly here, you might imagine this was survivable, but you continue downward, and the heat builds with increasing inevitability. The pressure intensifies. The air grows thicker, more viscous, as if you are sinking not through an atmosphere, but through something more akin to oil or liquid glass. The clouds envelop you completely now. There is no sky visible above you, no space, no void. There is only the yellow, the pressing density of it, the absolute darkness within the haze. At 40 kilometers altitude, the temperature has crossed the threshold into the uncomfortable. It approaches 100 degrees Celsius, the temperature at which water boils at sea level on Earth. The pressure is now growing acute. If you were actually present, your eardrums would be straining. Your bones would feel the weight of the atmosphere the way a deep-sea creature feels the weight of the ocean. But still you descend. The darkness intensifies, the yellow deepens, and the clouds acquire a new characteristic. They develop a subtle sense of corrosive presence. The sulfuric acid, no longer dispersed in mere traces, has become concentrated. It is still not liquid yet, not in the form of rain or droplets striking your skin, but it is potent. It fills the atmosphere not as a gas exactly, but as a pervasive chemical entity, a presence that would dissolve organic material if given the opportunity. 30 kilometers, 20. The temperature climbs past 120, 140, 160 degrees Celsius. The pressure has become almost unimaginable. It exceeds that of Earth's atmosphere by 90 times already, and you are still not at the surface. The clouds surround you in an oppressive embrace, and the golden yellow has darkened to something more like amber, occasionally tinged with orange where the heat becomes so intense that the sulfuric acid clouds seem to glow with their own internal light. The sensation of weight is no longer subtle. It presses from all directions with the force of something like 90 Earth atmospheres, equivalent to being 3 kilometers deep in Earth's oceans. Your body, were it flesh and blood, would be crushed. Your consciousness would be compressed. Yet still there is a strange serenity to it, a sense of inevitable descent into a world that has been sealed away from the wider cosmos by this impenetrable veil. 10 kilometers above the surface, the temperature approaches 300 degrees Celsius. The pressure exceeds 60 atmospheres. The clouds have thinned slightly, and for the first time, you begin to glimpse something other than yellow. The distant, rust-colored glow of the surface below, refracted and diffused through the dense atmosphere. The rocks, if you could see them clearly, would gleam with heat, and the landscape itself, broad volcanic plains, massive coronae like the footprints of ancient titans, vast networks of channels where lava once flowed like water, would shimmer with a strange, otherworldly radiance. The sulfuric acid clouds have reached their maximum concentration here, their maximum density. They form a layer so thick that it creates its own weather system, its own circulation patterns, independent of the rotation of the planet beneath. And finally, in your imagination, you reach the surface. The temperature is 465 degrees Celsius. That is nearly 500 degrees. That is hot enough to melt lead. The pressure is 92 times that of Earth's atmosphere, equivalent to the pressure 1,000 meters beneath Earth's ocean surface. The air is no longer breathable in any sense. It is almost liquid in its density, a strange soup of carbon dioxide, nitrogen, trace amounts of various compounds, and, constantly, the omnipresent sulfuric acid clouds above, forever separating the surface from any direct view of the sun or stars. The landscape beneath your feet is cratered, fractured, and in some regions nearly featureless. Ancient lava plains that stretch for thousands of kilometers. There are no rivers, no rain in any conventional sense. The sulfuric acid clouds do not rain water, but occasionally droplets of sulfuric acid condense and fall, only to evaporate again before reaching the surface due to the extreme heat. The world is silent. The winds are fierce in the upper atmosphere, but at the surface the movement is slow, ponderous, dreamlike. This is Venus. This is the world that orbits our sun as if it were born as Earth's twin, similar in size, similar in mass, cradled in the same stellar neighborhood. And yet it became this. What draws us to Venus, you might wonder, is precisely this contradiction, a world so close to us in size and proximity, yet so utterly transformed from whatever it once was. The mystery of how a planet could slip so thoroughly into chaos, while its twin Earth remained balanced on the edge of habitability, speaks to something deeper than mere planetary science. It touches on fate, on the delicate boundary between worlds that thrive and worlds that burn, on questions our species is only beginning to ask with real urgency. If you find yourself drawn to these slow, patient journeys through the strangest corners of our solar system, the kind that unfold without rushing, that linger on the scientific detail while honoring the profound mystery beneath it, then perhaps you might consider subscribing. Here, we move through the cosmos not as a checklist of facts, but as an unfolding story, a narrative of how worlds change, how atmospheres transform, how the difference between paradise and hell can hinge on variations so subtle they might have gone unnoticed had we not learned to read them in minerals and atmospheric traces and the faint geological record. Each journey is crafted with the same gentleness, the same commitment to accuracy tempered with wonder, the same willingness to sit with uncertainty when the science itself remains incomplete. Now, let us move backward through time, past the present hellscape we have already begun to understand, back toward the moment when Venus was still in the process of becoming itself. 4.5 billion years ago, our solar system was barely formed. The sun itself was younger, smaller, its light less fierce. Around it, in a disk of dust and gas that had begun to cool and collapse after the star's own ignition, planets were still assembling themselves through a process so gradual, so quiet, that it unfolded across millions of years without urgency or noise. Venus, the second sphere from the Sun, was gathering itself into being, one collision at a time, one coalescence after another, as planetesimals and protoplanetary bodies drew together through the patient work of gravity. Dust grains, no larger than a grain of sand, accreted into pebbles. Pebbles assembled into boulders. Boulders collided and merged and grew, again and again, until something vast enough to be called a planet had taken shape. It was a process both violent in its individual collisions and deeply serene in its overall rhythm, a kind of cosmic knitting, where the stitches were made of rock and the needles were gravity itself. In those early epochs, Venus would have been almost unimaginably hot, a molten sphere of silicate rock, its surface a roiling ocean of liquid stone. The heat came from multiple sources, all working in concert to maintain that infernal state. The collisions that built the planet, each releasing tremendous kinetic energy upon impact, added heat deep into the growing body. Radioactive isotopes embedded within the rock, uranium, thorium, potassium, decayed continuously, releasing warmth into the interior. The gravitational compression of the planet's own mass, pressing inward from all sides, generated internal friction and warmth. All of these processes worked together to keep Venus molten, to keep it in that state where solid and liquid were barely distinguishable, where the distinction between surface and interior held little meaning. And yet, even in that extreme state, something remarkable was beginning to happen. Gradually, slowly, over hundreds of millions of years, the surface of Venus began to cool. Heat radiated away into the vacuum of space, The outermost layers of that molten world began to solidify, forming a thin, dark crust that floated atop the still liquid interior below. A planet was being born, in the most literal sense, a solid world emerging from formless heat and chaos. What happened next is where Venus's story becomes most poignant, most mysterious, and most fiercely debated among those who study planetary evolution. For it is here, in the earliest chapters of Venus's existence as a solid world, that our knowledge becomes less certain. The evidence is faint, written in minerals that have long since transformed beyond recognition, recorded in a geological history that has been nearly erased. And yet scientists, working from models and from what little mineralogical evidence remains, have assembled a compelling case that young Venus may have been, for a time, a temperate world, a world with oceans, a world where water flowed, a world that, had you been able to stand on its surface 4 billion years ago, might have seemed almost familiar. 4.5 billion years before our present moment, in a region of space that would one day hold the sun and all its attending worlds, there existed something altogether different. Not quite matter, not quite void, a vast, rotating disk of gas and dust, turbulent with its own slow gravity, collapsing inward from a cloud that had itself been undisturbed for eons. This was the solar nebula, a place of gathering, where the universe was beginning to assemble itself into recognizable forms. Within this swirling geometry of particles and vapor, Venus did not suddenly appear. Instead, it grew. Grain by grain, pebble by pebble, the material that would become the second planet began its patient accretion from the surrounding disk. At first, these were microscopic specks of silicate dust, those infinitesimal building blocks that float between the stars. They collided, clung together through electrostatic forces barely perceptible to our modern instruments, and formed larger aggregates. Millimeters became centimeters. Centimeters became boulders rolling silently through an airless haze. This process unfolded over mere hundreds of thousands of years, a duration that seems impossibly long to us, yet was merely a blink in the solar system's youth. Each collision released a small amount of heat. Imagine the warmth of friction, gentle at first, accumulating across an inconceivable number of impacts. These kilometer-sized bodies, which astronomers call planetesimals, began to gather into larger clusters. They carved out zones within the nebula disk, gravitationally domineer their local neighborhoods, and swept up everything nearby. What began as solitary planetesimals soon assembled into what we might recognize as planetary embryos, bodies the size of the moon or larger, numbering in the dozens within what would eventually become the inner solar system. And one of these embryos, orbiting in that temperate zone between the scorching inner reaches and the frost-rich outer regions, would become our Venus. It occupied a special position, not too close to the forming sun, though certainly warm by the standards of a modern inner planet. Not so distant that it accumulated the volatile ices and lighter gases that would define Jupiter and Saturn. It was, in a sense, positioned in a nursery just right for something wondrous. The dust disk itself was slowly being depleted as the planets grew. Solar winds emanating from the infant sun, far more turbulent and energetic than the gentle stellar breeze we detect today, began to blow away the remaining nebula gas. This clearing process, occurring over perhaps 1 million years or so, meant that the window for planetary assembly was closing. The accretion disk that had lasted for so long was being erased. Venus, already substantial by this time, continued to collect whatever remained in its orbital vicinity, growing somewhat further, drawing the last fragments into its gravitational embrace. As the proto-Venus accumulated mass, its interior began to transform. The gravitational potential energy released by each infalling chunk of matter converted into heat. The bombardment of planetesimals and larger bodies struck the growing surface with tremendous force, each impact liberating energy in a flash of vaporized rock and incandescent debris. The deeper you traveled into this protoplanet, the more compressed the material became, and compression itself generates warmth. By the time the assembly was largely complete, Venus had begun to glow, not from any external source, but from the accumulated thermal energy of its own becoming. What was the temperature of Venus's surface during this epoch of assembly? It would have been far hotter than any world we might recognize today. Thousands of degrees, perhaps, molten, a sphere of liquid rock and metal, glowing faintly in the darkness, wrapped in a thin atmosphere of vaporized minerals released from its own crust. Yet it was not the hellish furnace of later ages. It was, in its way, serene, orderly, a world in the process of settling into itself. This is perhaps the most profound stillness in Venus's biography, the moment when it was complete enough to be called a planet, yet young enough that its fate had not yet been written. The solar nebula was gone, the age of planetesimals had ended. Venus hung in the black, alongside Mercury, Earth, Mars, and all the others, each waiting in its own orbit for whatever gravitational and thermal processes would come next. Each one, in that moment, possessed possibility. Each one carried within itself the potential for what it might yet become. Venus, in particular, remained largely unknown, a question mark suspended in the vacuum, about to undergo the slow transformations that would eventually write its extraordinary and tragic destiny. In those earliest epochs, when our solar system was still finding its shape, Venus began its long, patient cooling. Picture it, a world born from the collision of countless planetesimals, each impact releasing vast energies that kept the entire sphere glowing orange and white in the darkness of space. The young Venus was, for perhaps the first 100 million years of its existence, entirely molten. No solid ground, no water that could pool, just a roiling ocean of liquid rock, turning slowly beneath an atmosphere of its own vapors, iron oxide, silicates, gases boiling upward from the inferno below. And then, gradually, something profound began to happen. The radiation that had been poured into the planet during its violent formation started to escape, slowly, infinitesimally slowly by human measure, but with the patient inevitability that characterizes all planetary evolution. The outermost layer of that molten sphere began to cool. Atoms slowed their frenzied dance. Chemical bonds formed. Solidification began at the surface, spreading inward like a skin forming on cooling porridge, though this skin was hundreds of kilometers thick and took millions of years to consolidate. What emerged from this cooling was Venus's first crust, not the thin, fragile crust we see today, but a primitive carapace of dark, igneous rock, basalt and olivine-rich stone, the same kinds of materials that form the ocean floors of Earth. This early crust was volcanically active almost from the moment it solidified. Magma still churned beneath it. Volcanic outgassing released vast quantities of water vapor, carbon dioxide, nitrogen, and sulfur compounds from the planet's deep interior. The young world was still shedding its heat through 1,000 volcanic vents, still finding its equilibrium after its violent birth. Here, though, the narrative becomes more delicate, more speculative, and this is where the story grows quietly intriguing, because the geological evidence and the computer models suggest something that catches us by surprise when we think of Venus as it is today. As the crust continued to cool, over the course of perhaps 50 to 100 million years, the surface temperature may have gradually fallen below the boiling point of water, not to comfortable levels, not to the cool temperatures of Earth, but low enough, perhaps, that water could condense, low enough that the water vapor being released by volcanic outgassing could gather, accumulate, and eventually precipitate, rain, falling on a young Venus, collecting in basins, forming oceans, shallow seas pooling in the low places of that dark, volcanically restless crust. Is it true? Did Venus really have oceans in its youth? The question hangs in the space between certainty and speculation. No spacecraft has ever found direct fossil evidence of ancient Venusian water. We cannot bore into Venus's crust and examine its rocks with the intimacy we can with Earth's geology. And yet the models suggest it. The atmospheric chemistry hints at it. The mineralogy of Venus's high-altitude clouds contains clues that speak of a different past. Venus's early magnetic field, generated by a molten core with more vigor than it possesses today, might have protected a tenuous ocean and atmosphere from the solar wind's eroding touch, at least for a time. For perhaps 1 billion years, a vast span of time, yet only a fraction of Venus's 4.5 billion-year existence, the second planet from the Sun might have basked in a kind of temperate adolescence, not paradise. The greenhouse gases in the atmosphere would have made the climate warmer than Earth's, even then. The Sun, younger and slightly dimmer than it is now, would have shone on a world that was perhaps tropical rather than cool, but livable in the sense that liquid water persisted on the surface, in the sense that, if chemistry had aligned differently, if the mathematics of planetary fate had unfolded along a different path, Venus might have remained the home of oceans indefinitely. But the mathematics did not unfold that way. And here, suspended between these two images, the cooling sphere of molten rock and the younger world with lakes and seas reflecting a pale sun, is the true turning point of Venus's story. Somewhere in the transition from one state to the other, somewhere in that vast stretch of millions of years, the conditions were set for an irreversible transformation. The stage was being set, the actors were taking their positions, the feedback mechanisms that would, over the next few billion years, transform a potentially habitable world into an airless, scorched hellscape, were beginning their slow, implacable work. And the curious thing, the thing that makes Venus such a haunting object of study, is that we do not yet know with absolute certainty precisely when the first dominoes began to fall, or in exactly what order they toppled toward the catastrophe that was to come. What if Venus, in those first 1 billion years, was not so alien to our own world? What if, beneath that hellish sky, there once existed something almost recognizable, water in liquid form, pooling in low places, catching starlight on its surface? This possibility, though it exists now mostly in the realm of scientific modeling and careful inference rather than certainty, has quietly emerged from decades of planetary research as one of the most compelling chapters in Venus's biography. The evidence for this speculative past arrives primarily through two converging paths of investigation. The first comes from computer simulations, mathematical reconstructions built by planetologists who input the known physics of a young solar system and watch how worlds might have evolved under different conditions. These models suggest that in Venus's infancy, when the Sun was dimmer than it is today, the planet's surface temperature might have remained cool enough to permit water to persist in liquid form. Not an ocean as vast as Earth's, perhaps, but pools and seas nonetheless, spreading across the lowland basins that would later be buried beneath layers of younger lava. The simulations propose that Venus could have harbored a temperate climate, with water vapor rising into a thick but not yet runaway atmosphere, clouds forming and raining back down to the surface in a hydrological cycle not so terribly distant from the one that sustains life on Earth today. The second line of evidence emerges from mineralogy, the silent record written into rock. When water flows across silicate minerals over extended periods, it leaves chemical signatures. Certain ratios of isotopes, particular mineral assemblages, remain as witnesses to watery interactions with stone. Researchers studying the composition of Venus's atmosphere and the theoretical minerals that might exist on its surface have found tantalizing hints that weathering might have occurred, that water might have moved through the crust in the planet's youth. The detection of trace isotopes in Venus's upper atmosphere, particularly the ratio of deuterium to hydrogen, which is enriched in a way that suggests water was present long ago and has been slowly escaping ever since, provides a subtle but intriguing whisper from the past. Yet here lies the essential gentleness of this inquiry. We must hold these ideas lightly. We have never drilled into Venus's surface. We have never retrieved a rock sample that definitively proves ancient oceans once existed there. What we have instead are probabilities, educated extrapolations, the sound reasoning of atmospheric modelers and geochemists who have looked at the available clues and asked what scenario fits best. The truth is that Venus's surface has been largely resurfaced by volcanic activity over the eons, erasing much of the geological record that might have proved the case beyond doubt. In this way, Venus keeps her ancient secrets close. The possibility of early oceans remains compelling but fundamentally speculative, a hypothesis that seems increasingly likely to many in the scientific community, yet one that cannot quite be called proven. This uncertainty itself is worth contemplating as you drift deeper into stillness. The history of worlds is not always written in stone and certain fact. Sometimes it must be reconstructed from fragments, from the behavior of atoms and molecules, from the logic of physics applied across billions of years. Sometimes the most honest science acknowledges the limits of what we can know with absolute confidence, and says instead, given what we observe, this is what seems most probable. The young Venus might have had oceans, or it might have remained always parched, always hostile, always wreathed in thick clouds that kept the distant sun's warmth at bay. We cannot yet say for certain, but the question itself opens a door into the deep past, inviting us to imagine a world that might have been different, a Venus that might have taken another path entirely. And yet there exists a quieter force at work, one that shaped Venus's fate, not through any catastrophe of the planet itself, but through the slow, patient aging of the star it orbits. The sun, in the moments when we perceive it as eternal and unchanging, has been growing steadily brighter since the moment of its birth. This is not dramatic, it is not sudden, but measured across the billions of years that planets have existed, this brightening is profound. 4.6 billion years ago, when the solar system was still gathering itself from the cosmic dust, the young sun was perhaps 30% dimmer than it appears to us today. 30%, a figure so immense in its implications that it reshapes our understanding of why Venus became what it is. The star we see at noon, that golden disk of constancy, has been inexorably climbing in luminosity throughout the entire history of its worlds. This is stellar evolution speaking, the deep physics of hydrogen fusion gradually exhausting itself in the star's core, causing it to swell and intensify over time. In those early eons, when Venus was still cooling and darkening from its molten birth, the sun's gentler rays may have allowed the planet to retain liquid water on its surface. The habitable zone, that mathematical ring around any star where water can remain unfrozen and not boil away, extended inward toward the star in those days. Venus, despite its proximity to the sun, may have occupied a place within that zone, but the sun had an appointment with change. It does not pause, it does not negotiate, and as millions of years accumulated into hundreds of millions of years, that patient brightening continued. Picture it this way, if you will. Imagine standing at a window on a cloudless day, and having that room gradually illuminated by an ever-brightening lamp behind you, so slowly that you never consciously notice the change moment to moment. Yet by the time decades have passed, you realize the room has transformed. You can no longer read by the old daylight that once sufficed. The shadows are deeper, the brightness more insistent. The sun accomplished this transformation across Venus through the simple, inexorable mathematics of fusion. Scientists model this process with precision. The sun's luminosity increased in those early ages not capriciously, but according to well-understood principles of stellar physics. A star burning hydrogen gradually produces helium in its core, increasing the density there. To balance gravitational pressure, the core must burn hotter. A hotter core releases more energy. The surface must emit more light. This is not speculation but calculation, verified through observations of other stars at various stages of their lives. When we observe young stars in nearby stellar nurseries, we see dimmer versions of our own sun. When we observe older stars in their advanced ages, we see the pattern continuing. Our sun has followed this path as faithfully as any other. The implications for Venus were written into the stars themselves. As the sun brightened, more energy fell upon the young planet. More energy meant higher temperatures at the surface. Higher temperatures meant that any liquid water present began to evaporate more readily. And here is where a subtle threshold begins to matter. Once water begins to rise more substantially into the atmosphere as vapor, the problem compounds itself. Because water vapor is a greenhouse gas. It traps heat. The trapped heat causes more evaporation. The more evaporation, the more vapor in the air. The more vapor, the more trapped heat. This is the machinery of catastrophe in slow motion, and the sun's gradual brightening may have been the key that first set it in motion. What makes this particularly poignant is that Venus need not have been alone in this fate. Earth orbits farther from the sun and received less of that increasing energy. Farther from the star's brightening gaze, Earth's water may have been better insulated from the mounting thermal pressure. Yet Venus, positioned closer to the star at roughly 70% of Earth's distance from the sun, received that energy with an intensity that Earth never faced. The same stellar evolution that has sustained life on Earth for billions of years may have sealed Venus's transformation into an uninhabitable world. It is a reminder that a planet's destiny is not merely written by its own properties, but also by the changing nature of the star around which it orbits. There is something deeply humbling in recognizing that stellar evolution, this vast cosmic process unfolding across billions of years, would prove to be one of the primary authors of Venus's story. The planet did not choose its distance from the sun. The sun did not choose to brighten. These are the terms written by the physics of stellar nurseries and the fundamental architecture of stars themselves. And yet from these impersonal forces emerged a transformation so complete that an early Venus, had it possessed those temperate oceans and mild skies, would be unrecognizable to us now. The sun, in brightening, had begun a sentence that Venus would spend the next several billion years elaborating upon, with the planet's own processes taking up where stellar evolution left off, amplifying and accelerating the warming into a self-sustaining spiral from which no escape remained possible. As the sun grew brighter, slowly adding energy to the young solar system across those first billion years, Venus found itself in a position of terrible vulnerability. The planet orbited closer to that brightening star than Earth did, absorbing more of its growing warmth with each passing million years. And it was this proximity, combined with a simple but relentless physical mechanism, that would set Venus on its irreversible path. Picture the oceans that may have covered young Venus, those shallow seas beneath a thinner sky. They were not vast and deep like Earth's oceans, but they held water nonetheless. And water, you see, has a peculiar relationship with heat. When the surface temperature begins to rise, even slightly, the oceans do not remain passive. They begin to evaporate. Not all at once, but steadily, persistently, releasing water vapor into the atmosphere above. Water vapor itself is a greenhouse gas, a molecule that traps infrared radiation, that heat trying to escape back out into space. This is not a mysterious property. It is chemistry, fundamental and gentle, and it has been understood for more than a century now. So, as the brightening sun warmed Venus's surface by perhaps 5 or 10 degrees, the oceans released more water vapor, and as that water vapor accumulated in the atmosphere, it trapped more of the outgoing heat. The surface warmed further in response, and this warming caused more evaporation, more water vapor, more trapping, more warmth. This is the runaway greenhouse effect, and it is not a crash or a catastrophe in the moment. It is a slow, inexorable tightening of a spiral. Each increment of warming leads to more evaporation, which leads to thicker atmosphere, which leads to more warming still. The system feeds itself. The oceans do not disappear in a century or a millennium. They surrender themselves across hundreds of thousands of years, maybe millions, but the direction is set. There is no equilibrium to find. There is only the next step in the cycle, and the next, and the next. What makes this mechanism so powerful, so difficult to reverse, is that it operates on a threshold. Below a certain temperature, the water vapor in the upper atmosphere condenses, clouds form, rain falls, the water returns to the surface, and equilibrium persists. But once the temperature climbs beyond that threshold, and the precise number is debated among planetary scientists, though many models suggest somewhere between 40 and 60 degrees Celsius, the clouds no longer rain out. The water vapor rises higher and higher into the stratosphere, into regions where the air is thin and cold. And here is where the mechanism becomes irreversible. High in the stratosphere, where ultraviolet light from the sun is intense and unfiltered by the thick layers below, water molecules begin to break apart. A photon strikes the molecule, shattering it. Hydrogen atoms are liberated. Oxygen atoms are liberated. In the upper atmosphere, hydrogen is so light, so ephemeral, that it escapes. It drifts upward and outward, leaving the planet entirely. Some of it is caught by the solar wind and swept away into the interplanetary void. Some of it simply achieves escape velocity and never returns. Oxygen, being heavier, tends to remain, but it does not simply dissipate. It either combines with other elements or sinks back downward, eventually oxidizing rocks on the surface, a slow, subtle process happening over eons. The crucial point is this. Once the water vapor reaches the stratosphere and photodissociation begins, the process cannot be undone by cooling the surface again. The water is gone, molecule by molecule, escaping into space. Venus cannot recover its oceans. It cannot find its way back. Before this escape began in earnest, for perhaps several 100 million years, Venus was slowly strangling itself. The runaway greenhouse was in its early stages. The atmosphere was growing thicker with water vapor. The surface was growing hotter. The oceans were shrinking as their water rose into the sky. And still, from the perspective of a visitor standing on the surface, had any observer been there to witness it, the change would have seemed almost gentle. The sky would have grown hazier. The heat would have intensified gradually. The horizons would have blurred beneath thickening clouds. But what was happening in the upper atmosphere was the slow erasure of Venus's inheritance. Water that had fallen as rain for billions of years, water that had shaped the surface and perhaps harbored primitive chemistry, was being separated from itself. Hydrogen was being torn away, the bonds were breaking. And with each hydrogen atom that escaped, Venus lost a bit more of its capacity to sustain a moderate climate. The threshold, once crossed, allowed no turning back. Once the runaway greenhouse had truly begun, Venus entered a phase so gradual, so imperceptibly slow, that it might be called the planet's greatest exhalation. Picture, if you will, an ocean that had spent billions of years nestled in a cradle of rock and stone. Warm now, yes, but not yet boiling. And imagine that ocean gradually, inexorably, beginning to rise as vapor into the sky. The water that once covered perhaps the entire surface of Venus was no longer liquid. It had become something weightless and diffuse, a thick blanket of humidity suspended in an atmosphere grown hotter by the hour, hotter by the century, hotter across the slow march of millions of years. But here is where something extraordinary and almost melancholy began to unfold in Venus's upper atmosphere. High above the surface, where the pressure was thin and the ultraviolet light from the sun beat down with relentless intensity, those water molecules encountered radiation they could never withstand. A photon from the sun, a grain of light energy, would strike a molecule of H2O with enough force to tear it apart. This process, called photodissociation, split the water into its constituent parts, hydrogen and oxygen. The hydrogen atoms, being extraordinarily light and energetic, experienced something almost like liberation. They rose upward into the exosphere, that vague boundary between planetary atmosphere and the vacuum of space. And there they faced a choice, or rather, they faced physics. Some hydrogen atoms acquired enough speed, enough thermal energy, to escape Venus's gravity entirely. They simply flew away, up and out into the solar wind, never to return. One hydrogen atom after another, hundreds of millions of them streaming away across billions of years, in what might be imagined as a planet slowly exhaling its very essence into the void. The oxygen left behind, denser and more sluggish than its hydrogen partner, could not follow. It remained in Venus's atmosphere, sinking and dispersing into the lower layers, where it would participate in other chemical reactions, other slow transformations that we shall return to. But the hydrogen escape was relentless and inexorable. With each passing million years, Venus lost a little more hydrogen. With each passing geological age, the planet became a little drier, a little less hospitable to the kind of life that depends on abundant liquid water. The process was not violent or sudden. It was quiet. It was patient. It was, in some sense, the sound of an ocean vanishing not in a catastrophic boil, but in an endless, almost imperceptible evaporation that stretched across the ages. Imagine standing on the surface of Venus during those remote epochs, though of course no human could ever have done so, and watching the horizon gradually darken as the water vapor in the upper atmosphere increased. The sky would have grown hazier, the light more diffuse. Temperatures would have climbed in that steady, unhurried fashion that characterizes planetary climate shifts across geological time. The ground beneath your hypothetical feet would have grown warmer and warmer still. And all the while, at the edge of perception, at the very top of the atmosphere where sunlight tore apart H2O molecules by the trillion, hydrogen atoms were silently, ceaselessly escaping into space. The mechanism of hydrogen escape is itself worth pausing upon, for it is elegantly simple and profoundly consequential. The lightest element in the periodic table, hydrogen has virtually no anchor to planetary gravity once it achieves sufficient velocity. The sun's warmth provides that velocity. As the upper atmosphere of Venus grew hotter, heated by all that trapped infrared radiation, hydrogen molecules and atoms acquired more speed, more thermal motion. Some of them, the fastest moving ones, simply outran gravity's hold. They reached what physicists call escape velocity, that speed at which an object launched upward will never fall back down. For a planet like Venus, with modest gravity compared to Earth, and especially Jupiter, this escape was not rare or exceptional. It was routine. It was statistical inevitability. And so Venus wept hydrogen into the cosmos. Over 500 million years, over 1 billion, over 2 billion, the loss continued. Each water molecule that photodissociated contributed its hydrogen atom to that eternal stream fleeing outward. The numbers are almost incomprehensibly large. Modern scientific modeling suggests that Venus may have lost an amount of hydrogen equivalent to an ocean perhaps as deep and as vast as Earth's present oceans, perhaps deeper, perhaps many times over. Some models propose even more dramatic losses. The uncertainty is real, for we cannot directly observe what Venus was billions of years ago. We can only measure its present state and extrapolate backward through the physics we understand. Yet here is the profound sadness embedded in this process, if sadness can be attributed to planetary chemistry. Every hydrogen atom that escaped was one that could never be reunited with oxygen to form water again. The loss was unidirectional. It was irreversible across the timescale of planetary life. Venus was not merely losing water, it was losing the very possibility of having liquid water on its surface ever again. The atmospheric water vapor, the last traces of an ancient hydrological cycle, were being chemically disassembled and then physically ejected into space. What had once been an ocean was becoming nothing at all. It was becoming absence. It was becoming memory encoded only in geological signatures and in the calculations of astronomers and planetary scientists who would study this world billions of years hence. The hydrogen escape also had another subtle consequence, one that compounded Venus's fate. The process removed hydrogen from the planet's inventory but left oxygen behind. That oxygen, as we have noted, remained in the atmosphere, and as water vapor continued to dissociate and hydrogen continued to escape, the oxygen accumulated, dissolved, and participated in reactions with other compounds. Some of this oxygen would eventually combine with carbon that was being released as water had finished evaporating and silicate weathering had begun to slow. And thus, through this slow chemical rearrangement, the loss of hydrogen became inextricably linked to the buildup of carbon dioxide, that thickening blanket that would complete Venus's transformation into a hellscape. In a sense, Venus's loss of water and its accumulation of carbon dioxide were two sides of the same coin. They were not separate processes, but linked chapters in a long, slow tragedy of atmospheric chemistry. As the exosphere opened and hydrogen rushed away into the darkness, the lower atmosphere below grew thicker with carbon. The planet was not simply losing its water, it was trading one dominant atmospheric component for another. It was exchanging the possibility of temperate oceans for a suffocating blanket of carbon dioxide and heat. And it was doing so not in fits and starts, but in a gradual, patient fashion that stretched across hundreds of millions of years. The exhalation of hydrogen was the opening chord of Venus's final isolation, the beginning of the process that would lock it forever into the hellish state we observe today. As the young Venusian oceans began their retreat, something quieter and more relentless was already unfolding in the planet's rocky bones. The mechanism that had once held Venus in balance, the very process that regulates Earth's climate even now, was becoming a one-way door. On Earth, we have what scientists call the carbonate-silicate cycle. It is perhaps one of the most elegant feedback loops in planetary physics, though few of us have cause to think about it. When rain falls on rock, it carries carbon dioxide dissolved from the atmosphere. This weak acid, carbonic acid, slowly weathers silicate minerals, the feldspar and pyroxene that make up so much of our world's crust. This weathering releases calcium and other elements that eventually find their way to the oceans, where they precipitate out as limestone and other carbonate rocks. And these rocks, when subducted back into the mantle at plate boundaries, release their carbon dioxide again, completing the circle. It is a thermostat of sorts, a self-regulating mechanism that has kept Earth habitable for billions of years. When the atmosphere warms and holds more CO2, weathering accelerates, pulling that carbon back out of the air. When it cools, weathering slows. and CO2 accumulates again, the system tends toward balance. But on Venus, this balance had already been shattered. As the oceans evaporated and the water vapor rose into the upper atmosphere, where ultraviolet light from the sun broke it apart, the silicate weathering cycle began to fail. You see, weathering requires liquid water. It requires rain. It requires the patient, persistent work of weak acids against stone. Without oceans, without rainfall to speak of, this process ground nearly to a halt. Imagine a mechanism designed to regulate heat, suddenly finding itself without the fuel that powered it. The system didn't simply stall, it inverted. The carbon dioxide that had been locked away in rocks and carbonate deposits, the CO2 that might have been cycled back into the mantle and released slowly over geological time, began to accumulate in the atmosphere instead. With each passing million years, as volcanic outgassing continued and Venus remained geologically active, more carbon dioxide was added to an already thickening blanket. The atmosphere grew heavier, denser, more insistent, and as it did, the temperature climbed higher still. There is something almost poignant about this sequence, in the way of physical systems, a world caught in an escalating spiral, each cause feeding back into itself, each effect becoming a new cause. This was no longer a simple greenhouse effect, though it had begun that way. This was a runaway greenhouse, yes, but now compounded by the loss of the mechanism that might have arrested it. What planetary scientists sometimes call a positive feedback loop, though positive here means only that it reinforces itself, not that it tends toward anything desirable, had become the dominant rhythm of Venus's atmospheric history. The hotter the planet became, the less weathering occurred. The less weathering occurred, the more CO2 accumulated. The more CO2 accumulated, the hotter the planet became, around and around, tightening, intensifying, over hundreds of millions of years. Picture this slow, grinding acceleration, not a sudden catastrophe, but a patient, inexorable march toward extremity. The early history of Venus spanned perhaps 1 billion years or more from its formation, but the really decisive era, the time when its fate was sealed, when it crossed the threshold beyond which no return seemed possible. This took place over timescales we can scarcely perceive, hundreds of millions of years, increments so vast that human history seems like a breath taken in a single moment. The carbon dioxide thickened and thickened still, atmospheric pressure climbed, the greenhouse effect intensified, and somewhere in that slow, relentless accumulation, Venus's surface began to transform. The rocks themselves underwent subtle changes. As temperatures soared past what we might recognize as merely hot, 300 degrees, 350 degrees, and beyond, the minerals in the crust began to behave differently. Some compounds that had been stable for eons suddenly became unstable. Others broke down and released their volatiles. The question that planetary scientists sometimes ponder, quietly, is whether the surface itself became a source of additional CO2, as chemical reactions that had been dormant for millions of years suddenly awakened in the heat. And the oceans? Those ancient seas that may have once existed, that may have covered Venus in a temperate, almost hospitable phase of youth, they were long gone by now, evaporated, broken apart by ultraviolet radiation, lost to space. What had once been liquid water, a planetary treasure, a reservoir of possibility, had become dispersed atoms in the void between worlds. The carbon that had been locked in those waters, the carbon that might have formed carbonate rocks and been recycled slowly back into the mantle, had instead become part of the atmosphere, CO2 on a scale almost unimaginable, an ocean's worth of carbon, transformed into an invisible gas that pressed down on the planet with crushing weight and held in the heat with a stranglehold. Somewhere around this point, and here the certainty of our knowledge gives way to inference and modeling, to the patient work of scientists running simulations, Venus entered a state from which escape was, for practical purposes, impossible. The atmospheric pressure continued to climb, the temperature soared toward its current extremes, and the silicate weathering cycle, that elegant thermostat that regulates Earth and has allowed complex life to evolve here, remained essentially dormant. It could not function in an atmosphere so thick, so hot, so utterly alien to the conditions that permit the slow chemical conversation between rock and rain. What we see when we look at Venus today, that crushing pressure, that searing heat, that blanket of CO2 so dense and so insulating that it renders the surface invisible from orbit, this is the end point of that long, slow process. It is the consequence of a mechanism that was turned off, of a feedback loop that could not restore balance, of a world that spiraled inward toward extremity over the course of countless millions of years. And as we contemplate this distant, hellish world, we might pause to consider the fragility of the balance that sustains our own. The mechanisms that keep Earth temperate and habitable are not invulnerable. They are elegant, yes, and resilient in their own way. But they function within bounds. Push them too far, change the conditions too quickly, and even the most sophisticated natural thermostat can fail to keep pace with the forces arrayed against it. And yet beneath all this, beneath the suffocating weight of atmosphere and the chemical chaos of those clouds, lies a landscape shaped by forces so vast and prolonged that it seems almost unimaginable to us. Venus, in its way, has been quietly remade by fire, more times than we can certainly count. When we look down through the murk with radar, for no ordinary light can penetrate that haze, we find not the gentle rolling terrain of an old weathered world, but rather something far more dramatic. Vast plains of basalt stretch across the planetary surface, darkened lava flows that cover hundreds of thousands of square kilometers, as if the planet's interior has spent billions of years slowly painting its face with molten rock. These plains are not uniform. If you were somehow able to drift above them, which no human will ever do, you would see the landscape broken into regions of subtly different texture and tone. Some appear relatively smooth, their material deposited in waves, while others show the crinkled, fractured appearance of older flows that have been slightly disrupted by the trembling of the world beneath them. The transition zones between these regions are soft, gradual, suggesting not violent upheaval but something gentler, the slow overlap of successive volcanic episodes, one laid atop another, across millions or tens of millions of years. But what makes Venus's volcanic story truly strange, truly worth our attention as we drift through the darkness of these observations, is the presence of features that have no clear equivalent anywhere on Earth. Scattered across the planet's surface are thousands upon thousands of circular structures called coronae. Imagine a crown, a circular raised rim with a depressed center, sometimes with ridges radiating outward like spokes. No one is entirely certain how they form, which is itself a kind of gentle mystery. The leading hypothesis suggests they are the expression of deep plumes of hot material rising from within Venus's mantle, not unlike the plumes that create hotspot volcanoes on Earth, but on a scale that seems almost inconceivable. As this material wells upward, it swells the crust from beneath, pushing it upward and outward, creating that characteristic crown-like morphology. Some of these coronae may still be active, or may have been active relatively recently in geological time. There are other volcanic structures as well. Long chains of volcanic shields, their slopes gentler than the towering cones of the most dramatic volcanoes on Earth, suggesting flows of low-viscosity lava that travels far before cooling, steep-sided domes, and pancake-like formations, each one a record of a moment in Venus's thermal history. And everywhere, the lava plains themselves, rolling and vast, suggesting an almost incomprehensible volume of material that has poured from the interior and spread across the surface. What troubles many scientists, what makes them pause and think carefully about Venus's history, is a question that has no certain answer. These volcanic plains, these features spread across the planet, are they all roughly the same age, or do they represent a long, steady sequence of eruptions stretching back billions of years, the way we see on Earth, with its older volcanic rocks and its newer ones, layered in a kind of orderly sequence? The radar data we have gathered, particularly from the Magellan spacecraft in the early 1990s, suggests something perhaps more unsettling. The lack of extensive impact craters on Venus, compared to what we would expect if the surface were truly ancient, implies that the surface of Venus has been substantially renewed at some point. Not once, perhaps, but through multiple waves of resurfacing. Picture this for a moment. Over hundreds of millions of years, perhaps around 1 billion years ago, perhaps more recently, the timing remains unclear, Venus may have experienced a period of intense, globe-spanning volcanism. Lava flows moved across the land like slow, persistent tides, covering the older terrain, burying whatever may have come before. The craters left by ancient asteroid impacts, the record of billions of years of bombardment that should mark any world as ancient, were gradually obscured, filled, erased. A world's autobiography was written over. This is not a sudden explosion, not a catastrophic event, but rather something closer to a gradual forgetting. The planet's own heat, its own internal restlessness, slowly rewrote its surface. And if this happened once, there is no compelling reason to believe it could not have happened again, or that it is not, in some sense, still happening. We do not truly know how recently Venus's major resurfacing occurred. It could have been hundreds of millions of years ago, or something more recent in the vast sweep of planetary time. The question hovers there, unanswered, inviting speculation but demanding humility. Some researchers have proposed that Venus might have experienced episodic volcanism rather than the steady, continuous outpouring we see on Earth, with its mid-ocean ridges and its hotspots. Imagine the planet's interior slowly building pressure over a very long time, heat accumulating, the mantle growing increasingly restless, and then, at some threshold, a kind of release. Vast pulses of magma breaking through the crust, inundating continents of lava in relatively rapid succession on a planetary timescale, which might still mean millions of years. Then quiet, then pressure building again. The rhythm, if it exists, remains largely invisible to us, encoded in patterns we are only beginning to read. These lava plains and volcanic structures, the coronae and shields, and the vast flows of basalt, they are more than just landscape features. They are Venus's way of telling us about its interior. They are the expression of a world that has never cooled fully, never stilled itself into the dormant state that Mars has approached. Venus remains, even now, a dynamic world, still breathing heat from its depths, still driven by the churning of its molten heart. Whether it continues to erupt steadily or moves in slow pulses, whether it is slowly cooling or maintaining its thermal vigor through continued decay of radioactive elements, we do not know with certainty. But what we can say with confidence is that volcanic processes have shaped and reshaped Venus's surface across billions of years, layering the record, obscuring the past, keeping the planet young, in the sense that the evidence of its ancient epochs has been gradually effaced. And somewhere in that great overwriting, somewhere in those lava flows and in the heat that drives them, lies a piece of the answer to why Venus became what it is. The volcanoes did not cause the greenhouse effect, did not alone transform the world into a hellscape, but they may have sustained it. They may have kept feeding carbon dioxide into the atmosphere long after the water had fled to space, maintaining the pressure, maintaining the heat, preventing any possibility of recovery. The surface of Venus today exists in a state that pushes the limits of what we might still call a planetary surface at all. To understand what waits there, we might begin with heat, because heat is the first thing that would overwhelm you, though you would not survive long enough to truly feel it. 465 degrees Celsius. That is a temperature so far beyond the range of human experience that it exists almost in the realm of abstraction. To place this in perspective, the hottest naturally occurring place on Earth's surface, the Furnace Creek area in Death Valley, peaks at around 54 degrees Celsius. The hottest temperatures achieved in industrial furnaces, in kilns designed to melt steel and glass, approach 2,000 degrees. Venus's surface sits quietly between the two. It is hot enough that lead would melt, tin would become liquid, certain solder compounds, the metals that bind electronics together, would flow like water across the ground. And yet it is not so hot that rock itself becomes molten, as it was in Venus's violent youth. Instead, the stone beneath your feet, if you were somehow to stand there, would be perfectly solid, ancient and utterly stable. This heat does not come from the sun, though Venus orbits closer to the sun than Earth does, and receives more than twice the solar radiation. The thick atmosphere reflects much of that light back into space before it ever reaches ground level. The heat instead comes from below, from the weight of the atmosphere itself, and from the greenhouse gases trapped within it. The sun's energy enters, passes through that vast blanket of carbon dioxide and sulfuric acid vapor, reaches the surface, and when it tries to escape back toward space as infrared radiation, the atmosphere holds it. The heat bounces back down, again and again. A planetary oven with no escape valve, the air itself a conductor of warmth into every crevice and hollow of the stone. But heat alone is not what defines Venus. Pressure is the other dimension of its extremity, and it may be even more alien to contemplate. 92 bars of atmospheric pressure rests upon the surface of Venus. To feel the weight of 1 bar, you need only live at sea level on Earth. 1 bar is the standard atmospheric pressure we have evolved to withstand, to which our lungs have adapted, against which our eardrums are calibrated. 92 bars is 92 times that weight, pressing down on every square inch of terrain from above. Imagine descending into the ocean. As you sink deeper, the water above you grows heavier. Every 10 meters of depth adds another bar of pressure. At 100 meters down, you have experienced 10 bars of pressure. The deepest trenches of Earth's oceans, the Mariana Trench, reaches depths where the pressure is over 1,000 bars. But you would not need to go to such extremes to match Venus's surface conditions. You would need only to descend to 920 meters into the sea. There, in perpetual darkness, in a cold that would stop your heart within moments, in a place where the pressure would crush an ordinary submarine like an empty can, you would feel the same atmospheric weight that rests calmly upon Venus's burning rock. Combine this pressure with the heat. The air itself becomes dense, not like the thin wisps of atmosphere you might imagine, but like a fluid. It has weight. It has substance. If you were somehow transported to Venus's surface, protected in some theoretical suit that could withstand both the temperature and the crushing force, you might find that moving through the air itself would require effort. It would push back against you. It would resist your passage. The distinction between air and something more tangible would begin to blur. The pressure also affects chemistry in profound ways. Under such force, molecules behave differently. They bond differently. The sulfuric acid that drifts in Venus's clouds behaves with properties unlike sulfuric acid as we encounter it on Earth. The very rocks undergo subtle changes. Time, measured in geology, moves differently under such conditions. And yet, from a certain perspective, this is also stable. the surface of Venus does not experience the dramatic temperature swings that Earth does. There is no day and night as we understand it, because Venus rotates so slowly, and because the thick clouds obscure the sun entirely. There is no seasons, no weather in the traditional sense. Or rather, the weather is constant and unchanging, an eternal sameness that has persisted for millions of years. A visitor standing on that surface, if such a thing were possible, might look upward and see not a sky, but an opaque ceiling of murk. No stars, no sun, no horizon, nothing but a wall of bronze-colored clouds, thick and impenetrable, through which the faintest glow of sunlight might penetrate as diffuse illumination, without source or shadow. The pressure is so great that your bones might feel lighter, in a way. Gravity on Venus is actually slightly less than Earth's, about 90% of what you would experience here. But the atmospheric pressure would compress you, would squeeze you, would make the ordinary distinction between up and down somewhat academic. You would feel held, embraced, pressed upon from all directions with the weight of 92 atmospheres. And this is where the convergence becomes almost hypnotic to contemplate. The heat and the pressure are not separate phenomena, they are intertwined. The heat causes the gases to expand, which increases pressure, which holds in more heat, which allows the surface to grow warmer still. This is not violent. It is not chaotic. It is a deep, slow, patient equilibrium, an ancient balance that was struck hundreds of millions of years ago and has held firm ever since. Venus reached this state, this temperature, this pressure, and then, more or less, it stayed here, stable, silent, utterly inhospitable, and yet utterly unchanging. And so we arrive at the clouds themselves, those towering golden ramparts that have hidden Venus's face from human eyes for all of recorded history. They are not, as one might imagine, clouds of simple water vapor, for water, as we've learned, has long since departed. Instead, they are clouds of sulfuric acid, one of the most corrosive substances known to chemistry, suspended in layers that stretch from roughly 50 kilometers above the surface upward to about 70 kilometers, a vast cathedral of chemistry that exists nowhere else in the solar system that we know of. The formation of these clouds is a slow, relentless process born from the planet's extremity. Deep below, at the surface where the pressure could crush a human body instantly, sulfur dioxide rises from volcanic vents and emerges from the very rock itself, released by the heat and violence of a still restless world. This sulfur dioxide ascends through the thick atmosphere, rising slowly upward as thermal currents and convection carry it toward the cooler altitudes where clouds can form. And there, in those intermediate layers where the temperature drops to something more moderate, somewhere around 60 degrees Celsius, a subtle transformation occurs. Sulfur dioxide meets water molecules that have been produced through various chemical pathways, and together they form sulfuric acid, that yellowish, viscous compound that gives Venus its ghostly, shrouded appearance from space. It is worth pausing here to consider the chemistry as a kind of slow conversation between molecules. Sulfur dioxide is produced continuously, a consequence of the planet's internal heat and its sulfur-rich geology. Some of it condenses into droplets at higher altitudes where temperatures are lower still, perhaps 30 degrees or so, forming the visible clouds we might observe from orbit. And as these clouds exist, as they persist in their vast reservoirs, they participate in an ongoing cycle. Droplets of sulfuric acid occasionally fall toward the warmer layers below, where the heat is so intense that the sulfuric acid vaporizes back into sulfur dioxide and water vapor, which then reascend. The clouds, in this way, are not static monuments, but rather breathing entities, constantly exchanging molecules between the upper and lower atmosphere in a rhythm that has persisted for hundreds of millions of years. What makes Venus's cloud system even more peculiar is the manner in which those clouds circulate. The entire atmosphere of Venus moves in a way that seems almost impossible when first encountered. It rotates around the planet far faster than the planet itself rotates on its axis. Venus, as a world, completes one full rotation every 243 Earth days, a backwards rotation at that, moving from east to west rather than west to east as most planets do. Yet the clouds, the upper atmosphere, complete a circuit around the planet in just 4 Earth days. This is the superrotation, one of Venus's most haunting mysteries, and it means that a point on Venus's equator at the cloud top level moves at speeds exceeding 100 meters per second, a hurricane-force wind that never ceases, never rests, a perpetual gale that has probably endured since the planet's atmosphere thickened billions of years ago. How such winds arise is not entirely understood, though scientists have proposed several mechanisms over the decades. One possibility is that the enormous temperature difference between the day side of Venus, the side facing the Sun, and the night side creates pressure gradients so steep that the atmosphere is driven into rapid motion to try and equalize that heat, to smooth out the imbalance. Venus's slow rotation means that parts of the atmosphere are baked by sunlight for extended periods, while other regions fall into darkness, and the winds may be the planet's way of attempting, ceaselessly and unsuccessfully, to distribute that heat. Other models suggest that the cloud layers themselves absorb sunlight and re-radiate heat in ways that generate instability, spawning waves and eddies that cascade into large-scale circulation. The truth likely involves contributions from multiple mechanisms, a layered explanation that speaks to the subtlety of atmospheric dynamics, even, or perhaps especially, in extremity. This circulation has a structure, a pattern beneath the apparent chaos. At the equator, the winds are strongest, those prodigious 100-meter-per-second velocities that sound like sustained thunder. But as one moves toward the poles, the wind speeds gradually diminish, becoming less intense, more manageable in speed, though still formidable by any earthly standard. And there are also vertical currents, though they move more slowly, drawing air upward near the equator and allowing it to sink, to descend, at higher latitudes. Over the course of 4 Earth days, this global circulation carries the clouds around the entire planet, and then begins again, a rhythm as old as the thick atmosphere itself. Within these clouds, there exist phenomena we can only partially observe and incompletely understand. There are hints, in the ultraviolet light captured by spacecraft cameras, of mysterious dark patches and formations that suggest unknown chemical species, perhaps chlorine compounds or other sulfur oxides, substances that absorb ultraviolet radiation in ways that remain not fully characterized. What role these unknowns play, how they interact with the sulfuric acid clouds, whether they affect the chemistry or dynamics in ways that matter to the larger system, these are questions that linger. There is something deeply humbling about gazing at another world's clouds, knowing that for all our instruments and theories, the details remain partly veiled, partly mysterious, as though the planet itself preserves secrets that our science has not yet learned to ask for properly. And within this perpetual whirlwind of clouds, within these rivers of sulfuric acid moving relentlessly around the planet every 4 days, the surface below remains utterly still by comparison, dark, unreachable, a world that has become separate from its own sky, divorced from the circulation that occurs so far above. The clouds form a barrier, both physical and conceptual, between the alien hellscape below and the slowly turning void of space beyond. They are simultaneously Venus's face to the cosmos and its veil, revealing nothing of the secrets they conceal. And yet beneath all of this, beneath the crushing pressure and the golden clouds and the slow churn of that retrograde rotation, there exists another mystery, quieter perhaps than the furnace itself, but no less consequential. Venus has no magnetic field, or rather, it has only the faintest whisper of one, a magnetism so negligible that it might as well not exist at all. And this absence, this silence in the magnetic realm, opens a door into a process that may have accelerated Venus's transformation across billions of years in ways we are only beginning to understand. On Earth, our magnetic field wraps around us like an invisible guardian, generated deep within our iron core, where convection and rotation spin a great dynamo. This field deflects the solar wind, that constant stream of charged particles flowing outward from the sun, preventing it from tearing directly at our upper atmosphere. But Venus, it seems, has never managed to maintain such a shield. Scientists still debate the reasons why. Perhaps Venus lacks the rotation rate necessary to sustain a planetary dynamo, or perhaps, billions of years ago, some aspect of Venus's interior cooling or geological evolution shut down the mechanism that once generated a field. The questions remain open, unresolved, hanging in the darkness above that world. Without that magnetic protection, Venus's upper atmosphere has always been vulnerable to something called solar wind stripping. Imagine the sun's wind, relentless and patient, encountering Venus's ionosphere, that upper layer where ultraviolet radiation ionizes atoms and creates a population of charged particles. Without a magnetic field to deflect them, the solar wind particles can penetrate deep, collide with and energize the ionospheric material, and in doing so, impart enough energy to send some of those particles skyward, away from the planet entirely. It is a slow process, measured in grams per second, barely perceptible on the timescale of a human lifetime. But stretched across 4.5 billion years, this gentle stripping becomes profound. Consider what this means for a world that once, perhaps, held oceans. As the runaway greenhouse effect boiled those waters away and sent water vapor cascading upward through the atmosphere, Venus faced a critical vulnerability. In Earth's upper atmosphere, water molecules would be protected by our magnetic field, buffered against solar wind erosion. But Venus had no such shield. As ultraviolet light from the sun broke water molecules apart, a process called photodissociation, the resulting hydrogen atoms, being the lightest elements of all, would drift upward with particular ease. And there, in the ionosphere and exosphere, the solar wind would be waiting, ready to accelerate them further, to carry them away into the interplanetary void. One hydrogen atom at a time, Venus began to lose its water, not just to surface evaporation, but to space itself. This is sometimes called hydrogen escape, and it represents a permanent, irreversible loss, a one-way door that once opened can never be closed. The mystery of Venus's missing magnetic field thus becomes intertwined with the mystery of Venus's missing water. We cannot yet say with certainty which came first. Did Venus lose its dynamo early, leaving it defenseless against solar wind stripping even as it harbored oceans? Or did Venus retain its field long enough for those oceans to evaporate, only to lose the field later as its interior cooled? The evidence points in different directions depending on which models you trust. Some research suggests that Venus may have possessed a magnetic field in its youth, perhaps billions of years ago, before the planet's interior solidified and locked in place. Other work indicates that Venus may never have had a robust field at all, that its large size and slow rotation doomed it from the beginning to atmospheric vulnerability. What we do know with reasonable confidence is that this process, solar wind stripping, hydrogen escape, would have been far more significant on a Venus without magnetic protection than it would have been elsewhere. The same solar wind that brushed harmlessly against Earth's magnetosphere was, on Venus, a constant erosive force. And as the atmosphere became richer in carbon dioxide, as the pressure mounted and the temperature climbed, the loss of hydrogen meant that the ratios of atmospheric composition began to shift in ways that only reinforced the greenhouse catastrophe. More CO2 remained behind, less water vapor could escape to space. The atmosphere grew heavier, hotter, more hostile to anything we might call life. There is something poignant in this mechanism, something that speaks to the fragility of planetary destiny. Venus may have been undone, not by a single cataclysm, but by the quiet, patient erosion of its protective layers. Without a magnetic field, and perhaps without ever understanding fully why it lacked one, Venus became a world that could not retain its most precious element, the water that might have sustained oceans, that might have moderated the greenhouse effect, drifted away atom by atom, carried off by the solar wind into the dark. And with each atom that escaped, Venus's fate became a little more irreversible, locked into its present burning state by the cumulative weight of billions of years of atmospheric loss. It is a reminder that planetary environments are not simple or singular in their causes, but layered, interconnected, shaped by forces that operate on scales so vast and timescales so ancient that they seem almost beyond our grasp. And yet, there is something almost tragic about Venus's fate when you hold it alongside Earth. They are siblings, born from the same cosmic dust cloud at nearly the same moment in time, spinning in the same region of the young solar system. Both coalesced from the warm inner nebula, where rocky materials gathered into worlds. Both grew large enough to pull in dense atmospheres. Both possessed the chemistry and the warmth to support volatile cycles, the movement of water, the cycling of carbon, the slow breathing of a living planet. So why did one world flourish and the other transform into something so utterly inhospitable? The answer lies partly in the thin margins by which planetary fate is decided. Venus orbits roughly 30% closer to the Sun than Earth does. That proximity might seem like a small difference when measured against the vast emptiness of space, but in the physics of stellar heating, such distances compound into profound consequences. A planet 30% nearer to its star receives roughly twice the solar energy that a planet at Earth's distance receives. And as the young sun slowly brightened across its first billion years, a process astronomers call the faint young sun paradox, Venus absorbed that increasing radiance without mercy. The extra energy that Venus received was simply not something any planetary climate system could absorb without fundamental transformation. But there is another, perhaps equally critical divergence. Earth managed to retain vast oceans. Venus did not. This difference seems almost impossibly consequential when you consider the mechanisms that govern planetary temperature. Oceans are Earth's great thermostat. They absorb heat across their surfaces, distribute it through vast circulations, and release it back into space. They support a carbon cycle that pulls carbon dioxide from the atmosphere into shells and sediments, locking away atmospheric carbon in a slow, patient burial that has kept Earth's greenhouse effect in check for billions of years. Venus, stripped of its oceans, lost this critical regulating mechanism. Once the oceans were gone, boiled away and lost to space through the runaway greenhouse, there was nothing left to moderate the planet's fever. The atmosphere thickened unchecked. The temperature spiraled upward. There was no refuge, no buffer, no second chance. What is particularly poignant about this divergence is that both planets, in their youth, likely possessed the raw ingredients for habitability. Modern climate modeling suggests that young Earth, beneath its thicker early atmosphere, may have been warmer than it is now. Yet Earth remained temperate enough to hold liquid water. Venus's early atmosphere was probably not so dramatically different. It too may have had water vapor, nitrogen, perhaps carbon dioxide. The difference was that Venus was receiving too much heat, and the sun continued to grow brighter. When you trace the mathematics of Venus's atmospheric evolution backward through time, You can roughly estimate that the planet may have possessed surface water for its first 500 million years, perhaps even its first billion. It had the time, it had the chemistry, but it did not have the distance from its star. There is also the matter of plate tectonics, though here the story becomes more speculative and gently uncertain. Earth's surface is fundamentally shaped by the movement of vast crustal plates. These plates grind against one another, creating mountains, trenches, and the entire architecture of continental and oceanic geology. More importantly for climate, plate tectonics drives what geologists call the carbonate-silicate cycle. As rocks are weathered on Earth's surface, carbon dioxide is drawn from the atmosphere and locked into minerals. Those minerals are eventually carried down into the mantle through subduction, where heat releases the carbon dioxide, which rises again through volcanic eruptions. This cycle has operated for billions of years, and it acts as Earth's ultimate climate stabilizer. It prevents too much carbon dioxide from accumulating in the atmosphere, and it prevents too little from forming a runaway glaciation. Plate tectonics, in other words, is Earth's ancient climate control system. Venus, in its modern form, shows no evidence of active plate tectonics. Its surface appears to be covered by what is called stagnant lid tectonics, a single unbroken shell of rigid crust, with no large-scale subduction or spreading ridges. Whether Venus ever possessed plate tectonics in its early history remains genuinely uncertain. Some models suggest it may have, during those first few 100 million years when the planet was hotter and perhaps more geologically active. Others suggest that Venus's high temperature and thick crust may have prevented plate tectonics from ever establishing itself. What matters is that if Venus did lose plate tectonics early in its history, it lost access to the carbonate-silicate cycle that stabilizes Earth's climate. The carbon dioxide released by its evaporating oceans could not be efficiently recycled back into rocks. It accumulated in the atmosphere. The greenhouse thickened, the cycle accelerated. Consider the two worlds in their present state, Earth and Venus, separated by roughly 25 million miles of empty space. On Earth, the average surface temperature is around 15 degrees Celsius. The atmosphere consists mostly of nitrogen and oxygen, with relatively small amounts of carbon dioxide. There is water everywhere, oceans covering most of the planet's surface, water vapor in the atmosphere that regulates heat transfer, water locked into ice sheets and glaciers at the poles. The planet's rotation takes 24 hours. There is a magnetic field, generated deep within the planet, that shields the atmosphere from the solar wind, and there is an astonishing diversity of life, which itself feeds back into the climate system through countless biochemical cycles. On Venus, the surface temperature approaches 465 degrees Kelvin. The atmospheric pressure is 92 times that of Earth at sea level. The atmosphere is carbon dioxide, almost entirely, with traces of nitrogen and sulfuric acid clouds. There are no oceans. There is no liquid water anywhere on the visible surface. The planet rotates very slowly, backward compared to Earth, taking 243 Earth days to complete a single rotation. Its magnetic field, if it ever existed, is gone. The solar wind strikes the atmosphere directly, stripping away hydrogen and accelerating atmospheric loss. And yet, these are not two completely alien worlds. They are two versions of the same primordial story, told with different parameters, different distances from the star, different thresholds of climate sensitivity, different evolutionary pathways that, once chosen, locked each world into its trajectory. Earth was far enough from the Sun and blessed with enough geological and atmospheric complexity that it could remain temperate and retain its water. Venus was close enough and probably simple enough in its early climate regulation that it could not resist the heat. The runaway greenhouse seized hold. and it never let go. What makes this meditation on Venus and Earth particularly profound is the realization that the difference between a habitable world and a hellscape is sometimes merely a matter of distance and time. Given different orbital parameters, Earth could have been Venus. If our planet orbited 30% closer to the Sun, and if its early atmosphere had not developed robust feedback mechanisms to regulate temperature, Earth itself might have suffered a runaway greenhouse effect. The oceans might have boiled away. The magnetic field might have failed. We would not be here. Similarly, had Venus orbited just a little farther from the Sun, close enough to remain part of the inner solar system, but far enough to escape the worst of the stellar heat, it might have retained its oceans. It might have developed plate tectonics. It might be a world green with life and blue with water, as alive as Earth itself. This is a gentle, profound truth about planetary fate. The evolution of worlds is driven by physics, by the initial conditions set down in the solar nebula billions of years ago, by parameters both vast and infinitesimal. Venus and Earth are siblings not merely in the sense that they share a common origin, but in the deeper sense that they have both been shaped by forces far beyond their control. The only difference is that Earth happened to be born into circumstances where survival and habitability were possible. Venus was not. And in that difference lies the entire story of why one world remains a mystery to be explored, while the other remains home. And yet, for all the power of planetary science and mathematical modeling, we might never have grasped the true nature of Venus without the quiet, patient work of spacecraft, machines sent across the void to touch another world and return their whispered findings to us. The story begins in the Cold War, when the Soviet Union turned its gaze to Venus, not out of curiosity alone, but out of the profound drive to be first. Between 1961 and 1984, the Soviets launched more than 20 Venera probes, each one a small miracle of engineering, designed to survive, however briefly, in conditions that no human machine had ever confronted. The early missions burned up or crashed, their telemetry vanishing into the Venusian haze. But persistence, as it so often does, yielded knowledge. Venera 7, launched in 1970, became the first spacecraft to land on another planet and transmit data back to Earth. Its radio signal was faint, almost ghostly, but it arrived, a temperature reading of 475 degrees Celsius, a pressure measurement that spoke of a world pressed down by an invisible ocean of air. Humans now knew, not from theory, but from direct measurement, that Venus was a furnace. The later Venera probes grew bolder and more sophisticated. Venera 13 and 14, touching down in 1981 and 1982, carried cameras that managed to photograph the surface directly before their circuits surrendered to the heat. The images that returned showed a barren, rocky landscape bathed in a dull orange glow, the sky itself a pale, yellowish brown. The cameras lasted only an hour or two, but that hour was enough to show us, for the first time, what stood on Venus's actual ground. The soil samples returned slight hints of basaltic rock, evidence of ancient volcanism preserved in the chemical composition of dust that had never known rain or wind the way Earth's soil does. And the pressure readings, taken at the surface itself, confirmed what the models had predicted: 90 atmospheres, as if you were standing a kilometer deep in Earth's ocean. The machines themselves, inevitably, began to fail. Circuits crystallized, metal warped, and then silence. But by then, the Soviet Union had already given way to the Russian Federation, and the torch of Venusian exploration began to pass to other nations. In 1989 and 1990, NASA launched the Magellan spacecraft, which took up orbit around Venus and did something quieter than landing, yet no less revelatory. Magellan carried a radar instrument that could pierce the thick cloud cover and map the surface below in extraordinary detail. For 4 years, it circled the planet, building up a portrait of terrain that had never been seen directly by human eyes. The radar images showed vast lava plains, some younger than others, suggesting that volcanism had resurfaced large portions of Venus long after the runaway greenhouse effect had locked the planet into its current state. The maps revealed coronae, strange, circular features thought to be the result of upwelling mantle material, like vast calderas or volcanic crowns scattered across the landscape. Magellan's data suggested that Venus, far from being a geologically dead world, might be volcanically active still, perhaps erupting even now beneath those impenetrable clouds, reshaping itself in ways we can only infer. These images, when they came back to Earth, stirred something in the scientific imagination. They revealed a planet far more complex than the simple model of a runaway greenhouse effect might suggest. Venus became not just a cautionary tale of physics run amok, but a world with a history, a geography, a story written in lava and deformation. Then came decades of quieter observation. Japan's Akatsuki spacecraft, also known as Venus Climate Orbiter, reached Venus in 2015 after a remarkable journey that included a failed first attempt and a decade-long solar orbit before returning to try again. Akatsuki did not land or even approach the surface. Instead, it settled into orbit and began a patient study of the atmosphere itself. Its cameras, sensitive to infrared light and ultraviolet wavelengths invisible to human eyes, began to map the clouds with precision that no previous mission had achieved. Akatsuki revealed that the super-rotating winds, those strange, rapid movements of the upper atmosphere that had long puzzled scientists, were even more complex than anticipated. The probe tracked the motion of cloud features, measured wind speeds, and detected atmospheric waves and vortices that suggested the planet's air was in constant, churning motion. Most intriguingly, Akatsuki found hints of sulfuric acid aerosol variations that might indicate chemistry still unknown, processes still unfolding in that distant sky. Throughout these decades of exploration, a picture has emerged, not a complete picture, but a growing, intricate one. Each spacecraft has added a layer of understanding, a verification here, a mystery there. The Venera landers gave us ground truth. Magellan showed us the face of the world. Akatsuki is watching the breath of its atmosphere. And now, in the 2020s and 2030s, new probes are being prepared. NASA's Da Vinci mission, which may launch in the coming years, will send an atmospheric probe that will sample Venus's air as it descends, measuring the composition of clouds, searching for signs of past or present volcanic outgassing, perhaps even hunting for organic compounds that might hint at something we do not yet understand. Europe's Envision orbiter, also in preparation, will carry radar and spectrometers that promise to reveal the planet's geology and geological history in finer detail than Magellan could achieve. India's Shukrayaan-1 mission, similarly in the planning stages, reflects a growing global recognition that Venus, for all its hostility, remains one of the most important worlds in our solar system to understand. What strikes us, when we consider these missions and the long, patient decades of exploration they represent, is how much our knowledge of Venus rests on the shoulders of people we will never know. Engineers who designed instruments to survive impossible conditions. Scientists who interpreted signals and images returned from across millions of kilometers of space. Administrators who funded these journeys when the returns were uncertain. Venus was not conquered or mastered by a single brilliant insight. It was slowly, painstakingly revealed by human ingenuity applied across generations. Every photograph, every temperature reading, every wind measurement added a brushstroke to a portrait of a world that had been hidden from us, and that in many ways remains hidden still. And yet, in the slow accumulation of what we know about Venus, a particular thought begins to form quiet and persistent, like condensation gathering on glass. Here is a world that once may have harbored conditions not entirely unlike our own: water, perhaps a moderate climate, the possibility of something resembling habitability in those distant early epochs. And here is the same world now, wrapped in its caustic blanket, its surface a place where lead would soften and tin would melt, where the very chemistry of survival becomes an abstraction. The question that scientists have begun to pose, with careful deliberation and appropriate restraint, is whether Venus might speak to us not as a prediction of Earth's inevitable fate, but as an illustration of a threshold, a boundary between climates that sustain complex systems and those that extinguish them. The mechanism is not mysterious. As the young sun brightened over its first billion years, as stellar physics inexorably increased its luminous output, Venus found itself receiving incrementally more radiation than Earth. The difference, in the beginning, may have been subtle, perhaps only a few % of additional energy reaching its atmosphere. But physics operates without mercy on such margins. The extra warmth evaporated whatever oceans existed. Water vapor, lighter than air, rose into the upper atmosphere. There, ultraviolet radiation from the unshielded sun broke apart the water molecules. Hydrogen, the lightest element, escaped into space. Oxygen combined with surface rock or was carried away by solar wind. And so, over hundreds of millions of years, what might have been a planetary reservoir of water became dispersed into the cosmos, molecule by molecule, in an irreversible process that fundamentally altered Venus's chemical destiny. Now, here on Earth, we find ourselves in a different circumstance altogether, and yet one that invites serious reflection. We are not moving farther from the sun. We are not experiencing a runaway stellar brightening that will make our world suddenly inhospitable in a century. The solar physics that governs our star are well understood, and for the next few billion years, Earth will remain within what scientists call the habitable zone, that region where liquid water can persist on a planetary surface. And yet, the atmospheric composition of a world can be altered by mechanisms other than stellar evolution. Carbon dioxide and methane, the chief architects of terrestrial climate change, accumulate through processes we have long understood. They absorb heat that would otherwise radiate into space. They warm the lower atmosphere. They alter precipitation patterns, wind systems, ocean circulation. The mechanisms are not obscure. What makes Venus a useful, if sobering, mirror is not the idea that Earth will rapidly transform into a hellish twin. The conditions are fundamentally different, and the timeframes operate on entirely disparate scales. Venus lost its oceans over tens of millions of years through processes driven by stellar brightening and planetary physics beyond any civilization's control. But Venus does illustrate something true about planetary systems in general, that once a runaway greenhouse process begins, it possesses a kind of inertia. It feeds itself. The warmer the surface becomes, the more volatile compounds evaporate from soil and rock. The thicker the atmosphere grows, the more heat it traps. The more intense the solar radiation becomes, the faster photochemical processes accelerate. Each step makes the next step more likely, and somewhere along that cascade of feedback loops, a world can slip from a state of temperate complexity into something far simpler and harsher. For Earth, the analogy is not one of sudden transformation, but of trajectory. We are not in immediate danger of losing our oceans to space through photodissociation, as Venus did. But we are capable of triggering feedback mechanisms of our own. The melting of ice sheets that reduces planetary reflectivity, the thawing of permafrost that releases methane, the warming of oceans that reduces their capacity to absorb carbon dioxide, the multiplication of effects that reinforce one another over decades and centuries. And the humbling aspect of studying Venus, the thing that should anchor our thinking with quiet seriousness, is that we do not know with absolute precision where those thresholds lie. We do not know exactly how much warming would trigger which feedback mechanism with what intensity. The systems are enormously complex. The variables interact in ways that remain partially mysterious, even to those who have spent careers modeling them. This is where scientific honesty becomes essential, and where the study of Venus teaches us something about the limits of certainty. We can measure the current composition of Earth's atmosphere with exquisite accuracy. We can trace the history of carbon dioxide levels through ice cores and ocean sediments, spanning hundreds of thousands of years. We can build models that incorporate what we understand about planetary physics, radiative transfer, thermodynamics, and the behavior of fluids in rotating systems. And yet, even with all of this knowledge, there remain genuine uncertainties about climate sensitivity, about precisely how much warming will result from a given increase in atmospheric carbon dioxide. There are open questions about the role of clouds, about the timing of various feedback mechanisms, about regional variation and local extremity. None of this means we should be paralyzed by doubt. The broad direction of planetary response to increased greenhouse gases is established, and the risks are genuine and accumulating. But it does mean that anyone speaking with absolute certainty about exactly what Earth's climate will be in 100 years, or claiming to know the precise point beyond which no return exists, is speaking with more confidence than the science itself warrants. Venus, in this way, becomes a teacher not through providing a template for what will happen to Earth, but through demonstrating what planetary physics looks like when it operates without external restraint, when there are no homeostatic mechanisms to pull a world back from the brink, when a threshold is crossed and the systems begin to reinforce one another in an accelerating spiral. For Earth, the crucial distinction is that we possess agency. We can choose to understand the thresholds we are approaching. We can choose to measure and modify the atmospheric composition that determines our climate. We can choose to apply what we know to alter our trajectory, rather than passively watching as planetary systems cascade in ways we did not intend. Venus has no such agency. It cannot choose, cannot deliberate, cannot act. It simply exists in the state to which billions of years of planetary history have carried it. And perhaps that is what makes Venus simultaneously terrifying and instructive. Not because it is our inevitable future, but because it is a world that demonstrates what planetary extremity looks like when all choices have already been made, when all the decisions that determine a world's habitability have already accumulated into their final form. For Earth, the mirror is not one of fate, but of possibility, of paths not yet fully committed to, of thresholds not yet irreversibly crossed, of a moment in planetary history where understanding Venus gives us not dread, but rather a deeper recognition of what is at stake in the choices we make in the relatively brief centuries ahead. And so we arrive at the present moment on Venus, that shrouded world turning slowly in the vacuum of space, its day longer than its year, its rotation somehow reversed from nearly every other planet in our solar system, as if it had been knocked sideways long ago by some cosmic collision or gravitational dance we may never fully understand. Beneath those clouds of sulfuric acid that drift and swirl in perpetual winds, the surface remains largely unchanged from what it was perhaps 300 million years ago, when massive volcanic outpourings resurfaced the entire planet in a geological blink, erasing the record of everything that came before. We do not know if those volcanoes still stir in the deep places beneath that rust-colored crust, or if Venus has truly gone silent and still, locked in a kind of eternal, heated sleep from which it will never wake. The crushing weight of that atmosphere presses down with unimaginable force, 92 times heavier than Earth's own air at sea level. The temperature hovers around 465 degrees Celsius, hot enough to melt lead, hot enough that any visitor would be crushed and burned within moments, though we have briefly seen its surface through the cameras of the Venera probes, those brave little Soviet machines that sent back their precious photographs before succumbing to the heat. And yet there is something almost restful about imagining Venus now, eternally shrouded, eternally hidden, a world that keeps its secrets behind those impenetrable clouds. We have learned so much about it through instruments and mathematics and the patient work of scientists decoding radio signals from orbiting spacecraft, but there remains a profound mystery to Venus, a silence that seems to emanate from its surface even as the upper atmosphere races around the planet in a super-rotation that defies easy explanation. What quiets the mind about Venus is perhaps precisely that we cannot go there, cannot land and walk upon it, cannot speak to it as we might hope to speak to a world. It exists in our imagination and in our data, in models and simulations, and the accumulated photographs and spectrographs from missions spanning decades. It is a world that has become utterly alien, utterly transformed from whatever it might have been in that distant past, when it may have harbored water and perhaps the chemistry of life itself. And in that transformation, in that slow cooking and thickening and hardening, there is something that speaks to the fragility of worlds, to the delicate balance of conditions that allows a planet to remain habitable, to remain soft and wet and capable of change. Earth spins alongside Venus through the same solar system, warmed by the same sun, composed of the same elements forged in the hearts of dying stars, and yet one world remains verdant and alive, while the other has become a cauldron of chemistry and pressure, and an atmosphere so thick it would crush your bones. The difference, we know, was partly accident of orbital distance, partly the presence of water in greater abundance, partly the presence of a moon that stabilizes our axial tilt, partly a magnetic field that shields us from the solar wind's stripping force. But there remains something almost contingent about it all, something that whispers to us that Earth's own habitability is not guaranteed, that the conditions which allow us to thrive are precious and particular and, in the larger perspective of geological time, perhaps even temporary. And so Venus drifts on through the dark, covered in clouds that trap heat in an endless greenhouse, a thermal runaway that reached equilibrium billions of years ago and has since changed very slowly, if at all. The volcanic plains stretch endlessly across its surface, marked with strange formations called coronae, where heat rose from within the planet's interior and reshaped the crust in patterns we are still learning to interpret. The highland regions rise up in places, and great rifts scar the surface, but there is no water flowing through these canyons, no wind sculpting the rocks beyond what the extreme atmosphere might accomplish over millions of years. There is only the slow, steady press of heat and weight and chemistry, continuing its ancient reactions in the dark. Perhaps somewhere deep in the clouds, in those layers where the pressure and temperature are less extreme, there might exist some form of life, some chemistry we have not yet imagined, some adaptation to conditions so harsh that they would seem like pure fantasy to our terrestrial understanding. This remains speculation, a gentle whisper of possibility, but it is one that scientists continue to entertain because Venus is strange enough that we have learned to be humble in our expectations. The planet keeps its counsel, holds its secrets behind that impenetrable veil of sulfuric acid clouds, and in that silence there is a kind of peace. To contemplate Venus is to contemplate a world at rest, a world that has burned away its oceans and locked itself into a state of extreme equilibrium that will likely persist for billions of years more. It will continue to orbit the sun, continue to spin slowly in its backward rotation, continue to move through the darkness alongside Earth and Mars and all the other worlds. And in some distant future, when our own sun begins its slow transformation into a red giant, Venus will remain there as it is now, perhaps one of the last places in the solar system to be completely consumed by the expanding star, a world that was already hell long before anything else faced that final heat. There is a comfort in the finality of Venus, in knowing that some worlds have already experienced their ultimate transformation, that some fates have already been sealed and decided. Venus asks no more questions of itself. It has answered all the questions time could pose, and it rests now in the extremity of its condition, beautiful in its way, terrible in its way, but ultimately at peace with what it has become. The story of Venus is a story without an ending, without resolution or surprise, only the continuation of chemistry and pressure and heat, rotating slowly through the void, and in that absence of sudden change, there is a kind of lullaby, a soft and endless rhythm that echoes through the solar system, a gentle reminder that even in the harshest places, in the most transformed and alienated corners of our planetary neighborhood, there is something like rest, something like sleep, something like stillness,